Hello everyone, so welcome back, and in this segment we're going to talk about algorithm growth rates. All right, so how do we measure a algorithm's time requirement? We are going to measure the time requirement of an algorithm as a function of the problem size. Now, problem size depends on the application. Okay, problem size means number of elements we are going to consider to solve the problem. For example, let's say we're thinking about sorting algorithm. All right, so let's say we have to sort a set of items. Now, what is the size of the set of items? So there can be 100, or there can be 10,000 or millions of items. All right, so let's say we have a network, all right, say social network, and the number of users, okay, who is using the social network. And if we have to find a specific user, all right, in that case the input size is the number of users in that social network. So problem size depends on the application. Okay, so for example, let's say we have a problem with size n. All right, now let's say we have two algorithms to solve a same problem, solve one problem. All right, so algorithm A requires 5n square time units to solve the problem. Okay, and algorithm B requires 7n times 7n time units to solve the problem. All right, so let's see 5n square and 7n. Okay, so if n equals to 1, so looks like algorithm A is faster because time is 5, and algorithm B requires time is 7. Okay, now if n equals to 2, so in that case what happens? So 5 times 4, 20, and here 7 times n, 14. Okay, so when n equals to 2, we can see that algorithm B is faster. All right, so n equals to 1, algorithm A is faster. N equals to 2, algorithm B is faster. And n equals to any value which is greater than or equal to 2, you can actually check that. You will always find that algorithm B is faster. Algorithm B is going to be faster. Okay, now for a smaller input size, our algorithm, few algorithm may work better. Okay, but it's very important how a specific algorithm is working when our input size is increasing with a large number of input size. That's actually our main concern. So for the specific algorithm A, we are going to actually present that the algorithm A requires time proportional to n square. Okay, and algorithm B requires time proportional to n. So if we represent the time efficiency or time requirement like this, we can easily see that algorithm B is going to be faster. Always algorithm B is going to be faster. For a few amount of input size, like here n equals to 1, algorithm A may works better. But as algorithm B actually proportional to n, all right, so we are going to find actually a number of input size, all right, for which a number of input size for which or any number of input size greater than that, we'll find that algorithm B is going to work faster. All right, now this proportional time requirement, like n square n in this example we are talking about, is known as growth rate. All right, and when we are going to measure two algorithms, we are going to measure the efficiency of two algorithms by comparing their growth rate. Okay, also this is known as growth function. All right. So for algorithm A, the growth function is n square. For algorithm B, the growth function is n. All right. All right. Now let's see, we have two algorithm A and algorithm B. So algorithm A requires time n square by 5. All right. And algorithm B requires time 5 times n. All right. Now let's compare the efficiency of these two algorithms. Let's say n value equals to 10. Okay. So the runtime of A is 100 by 5, which is 20. Runtime of B is 5 times 100. Sorry, 5 times 10 actually, sorry. 5 times 10, n equals to 10, so which is 50. So seems like A is faster. Okay. Now even n equals to 20. So if n equals to 20, then 400 by 5, which is 80. B requires 5 times 20, which is 100. Still A is faster. Okay. But so here we are going to find a point for an input size when n becomes 25 or more than 25. Okay. So when n becomes 25 or more than 25, we're going to see that algorithm A is going to take more time than algorithm B. Means for any value greater than n value greater than 25, all right, we're going to see that algorithm B is going to work faster. So let's verify that. Let's say n equals to 25. Okay. Let's see 20, let's say 30. All right. So then the runtime of A is going to be 900 by 5. B is going to be 5 times 30. Okay. So here it is going to take like 180, and here it is going to take 150. Okay. So when n equals to 25, looks like they are going to take same amount of time, but for any value, okay, for any value where n is greater than 25, okay, let's compare that. Any value it's n is greater than 25, we're going to see that the runtime for B is going to be faster. Okay, runtime of B is going to be faster. And how we can be sure about that? So algorithm A requires n squared by 5. So we can actually express this like that. The runtime of algorithm A is proportional to n squared. Now, a plot of n squared is going to actually increase. It's like that. Okay. Now, if it's proportional to n, all right. So you can see that if it's proportional to n, it's actually a linear equation. So for a algorithm which is proportional to n, the total cost is going to look like, say, C1n plus C2. Okay, so the runtime function is going to be like this. So C1 is constant, C2 is constant, only n is the variable. Okay, so you can now see the equation of a line. A line equation is y equals to mx plus c. All right, m is constant, c is constant, x is the only variable. All right, so here this is a equation of line. So it's a linear equation. So if we increment this like this, it is going to grow like this. Okay, and it is going to grow like this. Now just think about any number of n, okay, greater than 25. Okay, a number of greater than 25. So this is for B, this is for A. So any number of n greater than 25, you'll see that algorithm B is going to work faster. All right. So here, why the growth rate is important. The growth rate is going to give us the idea how a algorithm works, okay, how a algorithm works with a increased amount of input, okay. So we are not only concerned about small number of input size, for example, 10, 100, 200, okay. We have to think about like that when the number of input is going to grow, all right. When it is going to grow, how my algorithm is going to work. If we find any point, okay, if we find any point like this, it can be 25 or 100 or 1000 or like 10,000, all right. If we find any point like this for which a algorithm is going to work better than the other algorithm, all right, we can find the efficient algorithm. All right. For example, here for a specific input size, you can see that algorithm B is always going to work better than algorithm A. So let's see a couple of more examples. So we have actually common growth rate or common growth function. All right. So common growth functions are represented as like C. C means constant. Constant means actually it's a certain amount of time. It doesn't matter how large the amount is, okay, or how small the amount is. Constant means it doesn't depend on the input size. All right, means it's a certain amount of time. Log n means logarithmic. Log square n is log squared n. N, we also say that it's linear. Okay, if a runtime is proportional to n, we're going to find the function is a linear function. It can be n log n, all right, it can be n square, read as quadratic, n cube, cubic, 2 to the power n. 2 to the power n is the worst one, and it's exponential. So let's see the runtime of each growth function for a small input. So let's say our input size is only 10. All right. So the constant runtime is always better if we find an algorithm which works in constant runtime. It means it's always better. Okay. All right. But in many cases, if we have actually input size and our algorithm depends on the input size, then let's compare the growth function which depends on the input size. So log x is the better. Log x is actually here, log x means log n. All right, n is the input size, is the best one. Okay, so here they are actually sorted according to the low runtime to high runtime. So log n is always the best approach of all the growth function that depends on the input size. Okay, then log square n is going to take a longer time than log n, then n, okay, then n log n, then n square, n cube, 2 to the power n, and 2 to the power n is the worst one. So here you can see that according to the runtime, you can see that this is for log x. Here x is our input size. Then we have, all right, so here the red one is the x. All right, the blue one is x log x. Now the pink one is x square, the yellow one is x cube, 2 to the power n. All right, so here from this you can already see that log x is better than x. Okay, x is better than x log x, obviously. Now for a small size of input, looks like x square and x cube is almost same. But let's increase the input size. Okay, if we increase the input size from 10 to 100, okay, we are going to see significant difference. So now our log x is actually a lot better because we can even see it here. It's almost like here. Okay, then we have x log x, and you can significantly find the difference between x square and x cube. All right, so that's how actually we can find the runtime of an algorithm. The runtime of an algorithm, we have to measure the runtime of the algorithm in terms of the input size. Okay, and we have to actually make sure that how our algorithm works when input size is growing. All right, so if algorithm A requires a time proportional to f of n, means a function of n is the input size. So we can say that algorithm A is said to be order of fn. Okay, and it is also denoted as order of, means capital O as f of n. So as we are using capital O, it can be also read as big O notation. Okay, we can also read this like big O of f of n. All right, now in our last example we saw that for algorithm A, it is proportional to n square. Okay, so here our function of n is n square. All right, so for algorithm A, we can say that algorithm A is to be order of big O of n square. Okay, so algorithm A has runtime order of n square. All right, now let's see algorithm A requires a time proportional to n. So that means f of n is n. Okay, and we can say that the algorithm A is order of n. Okay, or we can also say that it has runtime big O n. It's known as big O because we are using capital O, all right, capital O to denote the order of something. All right, so if it is proportional to, like, if the runtime is proportional to log n, all right, then we can say f of n is log n, and we can say that the runtime is order of log n. All right, so big O notation is actually very, very important, and it has some more significance. All right, the big O notation actually gives us the upper bound of runtime of the algorithm. All right, so what does upper bound means? Upper bound of runtime of the algorithm means that we can say that our algorithm is going to take at best this amount of time. All right, so when we are saying that the algorithm, the big O notation of algorithm is order of n square. Okay, so algorithm A has the order of n square. We can say that our algorithm is going to take at most, okay, at most n square of time. So big O notation is going to give us the upper bound of runtime of the algorithm. All right, so let's find the formal definition of the big O notation, okay, or order of an algorithm. Okay, so we say that algorithm A is order of fn, denoted as big O notation of fn. Now if there is a constant c exists such that a algorithm A requires no more than C of Fn time units to solve a problem of size n, okay, where n is greater than or equal to n naught. N naught denotes a initial size of input. And when we say that n greater than or equal to n naught, means we want to say that the value of n, actually the value of n means uh, a sufficiently large problems. All right. All right. So looks like a complicated definition, but it's not actually that complicated. Okay. So let's see, we have a function t of n. All right. So t of n is actually it's denoted as a runtime function. So if you remember initially, I mean, when we started our discussion, we calculated the runtime of an algorithm by using some rules, all right, by using some rules and by using the runtime of each instruction, okay. Now, for example, like if we have a nested loop, if we have a nested loop, the runtime looks like something like that. Say an square plus bn plus c. Okay, a is a constant, b is a constant, c is a constant. That's how we calculated the runtime function of a specific algorithm. Okay, all right. All right. Now I have an algorithm and I calculated the runtime like this. So can I actually make a statement something like that? Our runtime is proportional to n square. Okay. I can tell that my runtime is proportional to n square, means order of n square. Okay. That I can make a statement using the definition of order of Fn. Okay, so if an algorithm is proportional to a function f of n, this is denoted as order of f of n. All right. For example, here it is proportional to n square, so we can say that this is order of n square. All right. All right. Now, if I have a runtime function, this is a specific runtime function. Now, I can actually express this runtime function as an order of n square. Okay. All right. So, how I can do that? Let's read the formal definition of the order of order of fn of an algorithm. Okay. So I can say that an algorithm, let's say I have a runtime function Tn, okay, but I can say that an algorithm is order of Fn, okay, if there is a constant C, such as my algorithm A requires no more than C of Fn times unit to solve a problem, okay, where T of n, this is T of n, is always going to be less than or equal to C times f of n. All right. So let's see an example. So in this example, all right. So in this example, let's see, okay, so let's see here, value of Tn equals to n square minus 3n plus 10. Okay, so Tn is the runtime function. Okay, and we saw that actually how we can calculate the runtime function. So this is the specific runtime function Tn. All right. Now let's see, we can actually express this the runtime of the algorithm as a growth rate function, and in big O notation as like order of n square. Means we are going to represent that using a function of n equals to n square. Okay, what does that mean? Okay, means we have to have a c constant and a value of n, all right, which is greater than or equal to n naught. N naught means initial input size. Okay, for this c and n, we have to find, all right, that t of n will be always less than or equal to c times f of n. All right, don't think it as a complicated. So if we find any value of c and n for which this is going to be true, we can say that my algorithm A is order of f of n. All right. So let's see that whether I can express this algorithm with this runtime as order of n square. All right. Means here in this example, f of n is n square. All right. So for that, what do I need? I need a value of c and I need a value of n. And remember, for this, we can have actually multiple solution. I may have multiple values. I may find actually multiple values of c or multiple values of n for which I can find this condition true. Okay. All right. All right. So let's use c value equals to 3 and n value greater than or equal to 2. Okay, means n naught equals to 2. So for any value of n, if n value is greater than or equal to 2, let's find out. So then Tn is going to be n square minus 3n plus 10, all right? And f of n, or c times f of n is going to be 3 times n square. Okay. All right. So if n value is any value greater than or equal to 2. Okay. So let's find out. Let's see n value equals to 2. So if n value is 2, that is 4 minus 3 times 2, which is 6 plus 10. All right, so which is minus 2 plus 10, which is 8. All right, and here 3 times 4, which is 12. Okay, so for value of c equals to 3 and n value greater than or equal to 2, we can see that c times n square is greater than our t of n square minus 3n plus 10. All right, so for any value of n greater than or equal to 2 and c equals to 3, we can say that Tn will be always less than or equal to c times f of n. All right. So let's find out actually by using a plot. So this is the chart of our Tn. All right. Tn is the runtime function, and this is the plot for our Fn. Okay. Actually c times Fn. All right. So if we plot our runtime function like this, so this is our input size. Okay. So you can see that this is the point for any value, like let's say this is something, say 1.8. Okay, for any value n less than 1.8. Okay, so Tn is greater than c times f of n. Okay, but when the n value is greater than this point, okay, so you will find that, let's just increase this value, this function is going to grow like this, and this is going to grow like this, okay. So for any value n greater than this point, okay, you will see that this is going to grow faster. I mean, this is going to actually grow like this. This value is going to actually grow like this. This value is going to be, all right, so this value is going to be more than this, okay. So c times fn is always going to be t times t of n, okay, for n greater than or equal to 2. So what does that mean? So that means is that we're going to find a constant value c, or we're going to find a input size for which we can say that our algorithm is going to work at best, okay, at most our algorithm is going to work at most this amount of time, all right. So this is the absolute runtime. So minus 3 n square minus 3 n plus n, actually these values are not significant, okay. This constant value or the lower order terms are not significant in terms of the higher order terms, okay. You can see that this value is always going to be greater than this value, okay. F of n is always going to be greater than t of n. So I can tell that as to represent the upper bound runtime of an algorithm is that for a specific input size, okay, for a specific input size or greater than that size, our algorithm is always going to be at most this amount of time, okay. Our algorithm is going to take at most this fn amount of time, all right. So I can tell that the runtime is order of f of n, all right. So this gives us the upper bound runtime of the algorithm, okay. So knowing the upper bound runtime of algorithm is actually very important. So that gives us the worst case runtime of the algorithm, okay. So think about like any kind of appointment, okay. Say for example you are going to take a doctor appointment. Now a doctor appointment means it may take just like 10 to 15 minutes, okay. But generally an appointment, a doctor might actually tell you that just fixed a 40 minutes of time, okay. It is going to help you to make the arrangement, make the plans, like if you have some works to do, if you have some other works, okay. So for a specific appointment, okay, they may actually give you like a upper bound, okay. This upper bound 40 minutes means actually like it might take less than 40 minutes, but it is not going to take more than 40 minutes, okay. So this is the upper bound of the amount of time that an appointment might take, all right. So for an algorithm also, knowing the upper bound is important, okay. So when we're going to express the runtime of an algorithm using the upper bound, we can tell that this is the at most time, okay, our algorithm is going to take, all right. And it gives us actually the runtime in the worst case scenario, all right. So there is another example. I want to actually tell you that give here a pause, all right, and look at this problem and try to solve that by yourself, okay. So here we are saying that we have a specific runtime function tn equals to 2 to the power n plus 17, okay, and f of n is 2 to the power n. So can we represent this algorithm with Tn of runtime using order of 2 to the power n, means order of f of n. All right. So try to do that by yourself, and first try to do that by yourself, and then you can look at the answer here. All right.